Hello everyone, this is Victor, your host at StudyLab, and today we're continuing our exciting new series on how to make an operating system. And we're starting out by discussing assembly language, and obviously we're starting out with the very basics. So this will be a sub-series called Assembly Language 101, and this is part 1. Topics of discussion for today: binary data and data size terminology, CPU architectures 101, really just a few words here, something about registers and register size, CPU instruction sets, and memory and endianness. I'll also be giving you some reading material. So please check out the video description after you watch this video and check those out. Okay, so let's start with binary data and data size terminology. As I've said in the previous video, the only thing a computer basically understands is 0 and 1. Which actually translates into electrical impulses or voltage. So 0 means there's no voltage and 1 means some positive voltage. But let's start with 0 and 1. These are called bits. So 0 is a bit, 1 is a bit. It's the smallest amount of data that we're going to talk about when we reference computer data or binary data. So it's a binary digit. When you have a sequence of 4 bits, that's called a nibble. A series of 2 nibbles or 8 bits is 1 byte. A series of 2 bytes or 4 nibbles or 16 bits is called a word, and so on and so forth. So 2 words is 1 double word, 2 double words is 1 quad word, 2 quad words is 1 double quad word. Now, you'll also need to understand a little bit about binary and how to convert from one base to another. I'm not going to go into a lot of detail in this lesson, but I'm going to provide you with links that teach you binary in more detail. For now, let's just take a simple example. So let's say we have this byte or sequence of 8 bits, and the way we can convert this byte into base 10, which is the numbering system that we all use, is to start out from the right side to the left side, and with each step, so each operand here, we take a digit, a binary digit, so 1, and we multiply it by the base, which is base 2, because it's binary. And this base we need to raise to the power of the index of this digit. And the indexing starts with 0. So this is the 0th digit, this one is the first digit, this one is the second digit, third digit, and so on until you get to the 7th digit. So it starts with 0 and ends with 7. So, as I was saying, we start from right to left. So we have 1 multiplied by base 2 to the power of 0, which is the first index, plus this 1 here multiplied by the base 2 to the power of 1. Then plus 1 this third one here, multiplied by the base 2 raised to the power of 2, plus 1 multiplied by 2 raised to the power of 3, plus 0 times 2 raised to the power of 4, and so on until we get to this one here, which is the sixth. So this is 0, 1, 2, 3, 4, 5, and 6. So this is 1 times 2 to the power of 6 plus, and the final 0 times 2 to the power of 7. So I hope that makes sense, and if you calculate all of this, the result is 79 in base 10. So this whole thing here is the number 79. Now when we'll eventually start coding in assembly, we'll usually be working in hex or hexadecimal because it's much more compact and easier to work with than binary. So we need to know how to convert binary to hex. And I've included a simple table here that shows you how to convert one single hex digit into base 10. So from 0 to 9 they are equivalent. Then from 10 to 15 in base 10 you have A, B, C, D, E, F. So 10 in base 16 is A, 11 in base 16 is B, and so on. The way to convert this byte here into hex is to take each nibble, so each sequence of 4 bits, starting from the, well actually it doesn't matter where you start from. It's actually easier for you if you start from the left side. So say we start with this nibble here, which is 0, 1, 0, 0. Well, we can convert that into base 10 using this formula that I taught you here, and that result is 4 because it's this one, since it's 0 times 2 to the power of 0, and this is 0 times 2 to the power of 1, those are both 0. So the only positive term in this whole sum here would be 1 times 2 to the power of 2. So that's 4. So 4 in base 10 equals 4 in base 15. So we have our first digit. Then the last nibble is 1, 1, 1, 1, which in base 10 equals 15, which is basically the largest number that a nibble can hold. It's 15. And in base 16, that's F. So this byte here is 4F in base 16. Hopefully that made sense. CPU architectures. Okay, so CPU architectures are most often categorized based on their n-bitness. And what do I mean by n-bitness? Well, you often hear things like 16 bits, 32-bit, or 64-bit architectures, which generally speaking is n-bit architectures, right? That refers to, it basically refers to the size of the CPU registers. So a CPU which mostly uses 16-bit registers, so the maximum data that a register can hold is 16 bits. That would be a 16-bit architecture. But we never explained what a register is. So a register is a small data storing location inside a CPU. And that allows the CPU to do much faster data manipulation than accessing the RAM all the time. So what you could do is, for instance, you store a number in a CPU register, and then you store a second number in a second CPU register, and then you can multiply those two numbers. And when the CPU multiplies the numbers, it doesn't need to fetch anything from the RAM. It holds the data in itself. So it can do arithmetics much faster that way. So there are CPUs with 16-bit registers, CPUs with 32-bit registers, and CPUs with 64-bit registers for now. Most modern CPUs at the moment are 64-bit. There's also two main broad categories of CPU architectures called RISC and CISC. RISC basically translates to Reduced Instruction Set Computer, or CPU, and CISC is the Complex Instruction Set CPU. So a reduced instruction set CPU will have less instructions, so the number of instructions that it supports is less than the number of instructions that a CISC CPU would support. It has less instructions, and those instructions that it supports are more general, more abstract. So this has some advantages and some disadvantages. The main disadvantage would be that software using a RISC instruction set, software built for RISC CPUs, will have to execute more instructions to accomplish a complex task. So then that software will occupy more space, both in memory and on your hard drive. The advantage is that the hardware is more easier to build, and each instruction basically executes in one CPU cycle. And in some cases, they can be faster. If they're built right, they can be faster. But that's not always the case. In fact, right now, I think the Intel CPUs, which are CISC, are faster than most RISC-based CPUs. Obviously, they also had a lot more money to pour into research and development than their competition. So as I said, CISC means complex instruction set, so they provide more instructions, and those instructions can do more complex things. So they often take more than one CPU cycle to execute, and they execute a sequence of operations, actually, not just one atomic operation. And finally, we already talked about instruction sets. So instruction sets refers to the set of instructions that a CPU supports. And a different architecture often equates to different supported instruction sets. So an ARM CPU has different instructions than an Intel CPU, than an x86 CPU. I provide some links in the description where you can learn a lot more about CPU architectures and CPU instruction sets, on n-bitness and endianness and so on. So no worries about that. Sorry if it's a lot of information, but we'll take it slowly, and once we get into the coding, we'll be repeating some of these notions, so we'll be referring back to these. So no worries. Our focus on this class will be x86 CPUs, 16-bit x86, 32-bit x86, and 64-bit x86 processors. Basically AMD and Intel, really. And these are mostly CISC, and the reason I say mostly is that they're not pure CISC. They're more like a hybrid between RISC and CISC nowadays. Okay, and our last topic for today is a little talk on memory and endianness. And that's such a funny word, endianness. Anyway, let's look at this simple byte here. So a sequence of 8 bits. The right side, the most right side bit here in green is called the least significant bit, and the most left side bit is called the most significant bit. And you can think about it this way by taking a base 10 number as an example. For instance, 15. 15 has 2 digits, right? 1 and 5. Which one would you say that is the most significant digit? Well, it's obviously the left side digit, 1, because that refers to 10 out of 15, right? The 5 is less significant than 10. It holds less significance. So 5 would be the least significant decimal, and 1 would be the most significant decimal in 15. And the same thing happens here with this byte. So least significant bit on the right side, most significant bit on the left side. In the case of a word, so a sequence of 2 bytes, the least significant byte is on the right side, the most significant byte is on the left side. And why are we talking about words and bytes here? Because basically the least amount of data that you can store in memory is 1 byte. Not 1 bit, 1 byte. So if you imagine memory to be a collection of cells, 1 cell would be 1 byte in memory. So this is where endianness comes in. And it can refer, there's basically 2 notions, a little-endianness or little-endian and big-endian. First, just a little fun fact. Little-endian and big-endian comes from Gulliver's Travels. In that book, there was an episode where a civil war broke based on what the proper way was to break an egg, whether from the big end or from the little end. And someone took this funny little episode and coined these 2 terms, little-endian and big-endian, in computer science, I think in 1980. And anyway, little-endian refers to the way that words are saved in memory. And in a little-endian architecture, the least significant byte in a word would be saved lower in memory, and the most significant byte would be saved higher in memory. So you would read a word from memory from bottom to top. That's the direction, okay? In a big-endian architecture, the more significant byte is lower and the least significant byte is higher. So you read this from top to bottom, okay? Well, actually, it's the other way around, since the way we usually read numbers as humans is from left to right. So little-endian, since the least significant byte is lower, and we start reading numbers from the more significant digits. In a little-endian architecture, we read from top of the memory down, from top to down, okay? And in big-endian, from bottom to top. At the bottom you have the more significant byte, and at the top you have the less significant byte. So I hope that settles it. As I said, don't worry if you don't quite grasp all of this. You have the links in the video description to refer to, and I'm also going to be going through all of this again once we start coding and going through practical examples. So I think that's it for today, guys. I hope you enjoyed this. It's certainly useful for what we're about to do in our next lessons. So please pay attention, maybe watch this video again, take a look at the links in the description. Take your time with all of this, and don't forget to subscribe, of course. Until next time, have fun and keep learning.